Hello, it's Keith here, and today we're going to be looking at how to get a Hello World example working on the PC Engine, also known as the TurboGrafx-16. Now, unfortunately, it's also often known as that system no one's ever heard of because it was not a very popular system in some territories. In the UK, I'd never heard of it. In America, I think it made a little bit of traction, but no one really knew about it. In Japan, it was big. Boy, was it big. I've got a lot of PC Engine stuff, but as I say, before I came to Japan, didn't know anything about it, didn't really care either, which is a real shame because, to be honest, the PC Engine is a great middle ground between the 6502 systems. It's very powerful. It's only 8-bit. It's not got any of the Super Nintendo 16-bit weirdness. It's got a simple sound chip. It's got easier graphics than the NES and better graphics than the NES by miles. It's a really decent system if you want to get started on a 6502 system. That said, it's not technically a 6502, it's a 6280, and it's got some weird commands, which we'll look at today. But while they're weird, once you get used to them, they're not nothing to worry about. And as I say, it's an 8-bit processor, but it's a very fast 8-bit processor. So anyway, let's have a look at the code and let's see what we're going to be working on today. So, we're going to be doing Hello World, as we always do. And let's fire it up and let's just see that I can deliver the goods, because otherwise we're not going to be having a very long tutorial today, are we? And there we go, there's a nice Hello World for you. So we can see our code running on the PC Engine here, and let's see what we've been doing. So our cartridge starts E000 here. Now our cartridge doesn't really have a header, but if you look at the very bottom, it does kind of have a footer just here. And you can see there's a pointer to the program start. And you can see the program starts. It's just the first line of our code. Now, at first we are setting the interrupts to be turned off. We're enabling high speed mode because the CPU can run pretty fast. It can run at, I think it's 6 megahertz or 1.5. Now this may relate to the handheld version, but for whatever reason they did have 2 speeds, but let's have all that speed. Let's take full advantage. And we're just disabling decimal mode here. Now what we're doing next is a little bit tricky. I'm not going to go into it in great detail, but we're banking in the memory of the system, the ROM and the RAM. We've got these special TAM commands. I'm not going to go into it at this stage, just you can use them as is. And this is going to be something quite important. You can't assemble this with a plain 6502 assembler. You're going to have to have something a bit better. Now you can trick a 6502 assembler by defining some macros with some bytes in them, but probably too much if you're just starting out. Anyway, so at this point we've paged in our memory. We're initializing our stack pointer here. And we're setting some interrupt masks here, but this is where our code's really going to start here. So here we're turning on our background here. We're defining our tilemap size, and you can see we're using these commands ST0, ST1, and ST2. Well, those aren't 6502 commands, are they? Well, again, just like the TAM, they're a 6280 command. And what they are is ST0 stores a register value, and it selects a register within the video hardware. ST1 sets a value to that register, and ST2 sets the second value because this is a 16-bit pair. Now here's the thing though, these only work with fixed values, so you can't use the accumulator in this context. We'll see that later. So these are only if the value you want to set is fixed. So register 5 here is defining the video options here. Register 9 is selecting the tilemap size. 7 is the X scroll of the tilemap. And 8 is the Y scroll here, so we're just setting up the tilemap so that the first tile in the top left corner is the first tile in the data area, just to make things nice and easy. We're then going to set up the palette. I'm only going to use 2 colours today. The background I define as blue in all of my tutorials, and you can see we're doing that just here. And then I'm defining colour 15 as the font colour. I have used the top colour as a font, and this is a 16 colour system, you see. So the background, we're just selecting palette entry 0 here. And we're just setting the blue component here by setting A to these 3 bits and then storing that in 404, and then setting the green part in 405. You can see here we've got 3 bits per channel. So we're selecting here color 0 with this pair, and then we're selecting it to blue with this pair. When it comes to color 15, we're writing a 15 to 0402 and then 0 to 0403. I think it's 512 colors in total that the PC Engine can have. It's a lot of colors. As I say, it's a very nice system, really underrated. And then once we've selected our color entry, we're setting this to yellow. So we're setting all of these 3 blue bits to 0 here, and the 3 bits of red and green to 1s here, and we're writing those to 0404 and 0405. And that has set us 2 colors just to do the basics of our font. Okay, Now, we want to define our font, don't we? We're going to this time be doing things a little bit differently. But first of all, we're going to select register 0, which is the data port register, and we're selecting the address we want to write to. We want to write to memory address 1000, so we select the data port with this ST0 here, and we select that as port 0, and that's selecting register 0, which is the data address. And then we write the low byte, which is 00, and the high byte, which is 10, and we use ST1 and ST2 there. Now we select register 2. Now register 2 is actually the receiver of the data that's going to go into the memory address selected with register 0. If I remember correctly, register 1 is a read address, register 2 is a write address. So we're writing to that address we selected here. We're then loading the address of our bitmap font. There are 96 characters in our bitmap font, and there are 8 lines for each because it's a black and white font. So we've got a total of 768 bytes to write, and we're using X and Y to count those. Now we are having to do 2 pairs of bit planes here. A 16 color pixel will use 4 bits to define it, and rather than have those 4 bits in one nibble, they're actually all split out. So one byte will contain all the bit zeros from 8 consecutive pixels. The next byte will be all the bit ones from 8 consecutive pixels, and then the same for 2 and bit 3. A bit weird, I know, but that's the way these things tend to work. And on the PC Engine, for whatever reason, bit plane 0 and 1 are clustered together, and 2 and 3 are clustered together. So to convert our black and white font into a color 0 or color 15 font, we're writing all the lines of the fonts to all 4 bit planes. And so we're doing this with these 2 commands just here. So this will write 2 of the bit planes. Now, effectively, what we would want to do is write to ST1 and ST2 here. But remember, they can only take fixed values. So we're using the memory mapped addressed equivalent of those, which is 1002 and 1003. For your reference, 100 would be ST0's equivalent. Now, I know you probably don't know what that means, and maybe it's confusing you. If it is, just check out the platform specific series. I went over this in a bit more detail, and there's some simple charts on my website as well that maybe will help you out. But as I said before, just use this. It's really intended to just use this code as is and just have a play with it. It's not intended as much more than that, because as I say, you can go into the platform specific series if you want to get into the nitty gritty of it. So we're loading in a line of our font in black and white, and we're storing it to both of the bit planes by writing to 102 and 103 here. And that will do that. We then repeat for the 8 lines of the character. Effectively, we will then return. Where do we go? Here we go. And then we do the same for bit planes 2 and 3. And then we're just checking if Y has reached 0. If it's not, we just loop back up here. If it has, we increment the high byte of our font address here, because we're storing that in 60 and 61 here in the 0 page. And once we get to here, we've actually finished setting up our screen. Here we're just clearing the screen. You can see here we're loading VDP address 0 here. And that is the start of the visible tile map. So that's the patterns that are selected to be shown on the screen. So we're selecting register 0. We're selecting we want to write to memory address 00 here. And then we're selecting register 2 again, because we now want to write. But this time we can write just very simply here by using ST1 to set the high byte to 0 and ST2 to set the low byte to 1. And so this time we're using fixed values, so we can use ST1 here. We set the low byte to 0 and then the high byte to 1. Now this effectively sets all of the tiles to tile number 256. And the reason for that is that our font was actually loaded into tile 256. Why didn't we start at 0? Well, all of the memory map is overlapping itself. So tile 0 is actually also the data that's defining the visible areas of the screen. It's a bit weird. Rather than slicing certain areas, this is the tile map, this is the pattern map of the tile data. They're all the same data range, so tile 0 is unusable in effect, at least in the way things are set up. So that's why we're starting from tile 256 here, and that's why we set the high byte to 1 and the low byte to 0 to select the first tile from our patterns that we defined in our font. Okay, so we're now ready to actually draw to the screen. So let's see how we're doing our print character routine. And here it is. Now, the tile map, as I say, starts at 0. And so we've got some fairly simple calculations to do to work out what the address we want to write to in our tile map is. We've got a cursor X and a cursor Y here. These are 0 page entries that we use to remember where we're drawing to next in our next character as we print to the screen. If you think of the locate command, locate selects a character, and then the print command will draw the character to the previously located position, and automatically increment, and that's what this does. So to calculate the address we want to write to next, we effectively want to multiply the wide position by 32, because we've defined our tilemap as 32 wide. Can be wider on the PC Engine, but that's what we've defined in this example. And then we want to add our X position, and because the tilemap starts at memory address 0, there's nothing else to add. The way we do this is with bit shifting. Whenever we shift to the left a byte, we're effectively doubling it. So we split our Y position up into two parts here, and we're effectively calculating the low part here and the high part here. And of course with the low part, we're having to add the X position just here as well. But this write to 102 and 103 here is, because of this write selecting register 0 here, is defining the address that we want to write the next data to. Now we pushed onto the stack the accumulator here, and now we get it back, and this is the character we want to show to the screen. We now want to write data, so instead of selecting register 0, we now need to select register 2. And then we're subtracting 32 from the character we want to show. This is because there is no characters below 32 in our font. 32 is space. Effectively, it's actually character 256, and that's why when we wrote up here, we were writing character 256 to the screen to clear the screen, because that's the space character. But it means we have no characters below 32, and we need to do a subtraction. We've now calculated the pattern that we want to show in that tilemap position, and we've selected the tilemap position to write to with these commands here. So all we do is we store that value from the accumulator by writing to memory address 102 here, and then we want to make sure that it's not pattern 0, 1 or 2, because as I say, everything below 256 is unusable. So we have to add 256, and so we store the high byte as 1 here, and we're doing that here. Now we could do the same thing by doing LDA #1 and then STA $0102 here. That would have the exact same effect, but it's a lot more commands. So we're using the 6280 command here, ST2 here, to write that fixed value to that memory address there. Once we've set our character on the screen, we now need to update our X position, incrementing it, checking if we've got to the end of the line, and using a new line command if we have. And the new line command is very simple. We're using the 65CO2 command, which exists on the 6280, to 0 the X position and incrementing the Y position. So we get a character to the screen anyway. Now, in my tutorials, I always use the same print string routine in all of them. What we use is a 255 character terminated string, and we just read in all of the characters until we get to a 255 and print them to the screen, just repeating using Y as a counter. And you can see that being used here. So we're loading the high byte of the hello world address into 61, the low byte into 60 in the 0 page, and we're running print string, and then we're just starting a new line. And you've seen the result of that just there. It's a bit of a pain, and I know the 6280 commands are a bit confusing, but as I say, for its sins, the PC Engine is a lot simpler than the Super Nintendo or the NES. On the NES, we have to worry about whether we're in VBlank to update the screen, and on the Super Nintendo, if you're going to do sound programming, then you've got the SPC 700 to fare with, and good luck with that. And as I say, the PC Engine is much more similar to the 6502 than the 65816 is. So, you know, I would personally strongly recommend it as an easy system to get started with for some nice 16-bit quality graphics in the 6502 range, 68,000 range, probably the Genesis, but anyway. So that's the simple Hello World example. Now in my tutorials, we always follow Hello World with a little bit larger example. We add a few extra lines and we show some monitor tools, a memory dump and a register showing routine, and these are intended to help you out if you're just getting started with the system. Now it's a little bit complicated. I'm not going to go into the details of how this one works, but we've just had to include a few extra commands here at the top and bottom, and that should be enough to get these monitor tools running. And then where are the monitor tools? They're just here. We've got a command monitor which will dump the registers, and a command memdump which will show some of the memory to the screen. So let's fire that up and see it running now. And here it is. So we've got our hello world as before. Now we've got the accumulator shown, X register, Y register, stack pointer, flags, the program counter, and a bit of memory just here. So if you're having problems with your system and things aren't going quite as you'd expect, well, these may help you out and just allow you to see a little bit of what's going on under the hood and just maybe figure out where things are going wrong. For example, if we want to just double check our cartridge is loaded into the memory address we think it is, well, we can now dump our cartridge straight to the screen here and just see the contents of it. So as I say, these are just intended as a little bit of a help because a lot of the emulators don't have the monitor tools we might prefer them to, and I find it's easier to write your own than to just rely on stuff that may or may not be present if you're programming a lot of systems. It's also a lot of fun writing them, and I find it quite satisfying. But anyway, if there's some use to you, then there they are, and if they're not, just forget about them. All of these examples are totally downloadable from my website. All the tools I use as well, the pre-compiled VASM assemblies, and all of these scripts as well. So if they help you, just go ahead and download them. But if you want to do things yourself, then that's great. You know, if you find anything useful in these tutorials, just take the bits that you find interesting and then just start with your own stuff. That's, if you've got the confidence to do that, that's terrific. Now, I'm going to show you the script that I used to build today's example. It's pretty straightforward, but again, this is another thing that if you're not familiar with this stuff and you don't know where to start, could take you a lot of time to figure out, and it all just gets in the way when you really want to be seeing some progress to start with. So let's have a look at the code I'm using. So I'm using the 6502 version of VASM, which the author was very kind and added the 6280 extensions to for me. Very, very kind gentleman there. So we're specifying the name of the source file, this %1, because it's a batch file. This will be the helloworld.asm file. We're specifying 6280, which turns on the extra commands of the 6280. Also enables the 65CO2 commands, which the 6280 has. We're telling the assembler to check labels. This is something that's quite handy. If you make a mistake and you forget to put the tabs on one of your commands, for example, if I do that, PHX will now be being treated as a label, and that's going to cause a crash, almost certainly. So by enabling that option, the assembler will say, hey, I'm pretty sure you just did something silly there, and it will save you a lot of time because it almost certainly is something pretty silly. You certainly don't want to intentionally name labels with the same names as commands because some assemblers wouldn't compile it at all, I don't think. So we're then specifying to disable case sensitivity. It just makes my life easier. I'm a Windows person, not used to case sensitivity enough. I know it's better to be strict with your case, but takes a lot of time and a lot of debugging, so I'm sorry, I'm currently not that strict with it. I'm specifying a symbol defined as VASM. I do this just in case I need to change assemblers later. It allows me to have conditional code, parts that are assembled for different assemblers. I'm also defining a symbol called build PCE. I think the monitor tools may need this, but the Hello World example doesn't, so don't worry about that if you're just doing the simple one. I'm outputting a listing file. This is a debugging script. It will show all of the source file and all of the destination bytes that will resulting in the compilation. And this is going to be helpful if you're having trouble. I found it very good in the 68000 series because there were some commands that weren't working as I expected, and I found out it was actually built-in optimization in the assembler. Also, sometimes if you're using labels and weird mathematics, it's possible you've managed to confuse the assembler and the maths isn't working out the way you think it's going to. In the early days, you probably won't need it, but it's a good thing to have if your assembler can output it, so I'd certainly suggest that. The important bits, though, are we're outputting a binary file, and we're specifying the name of the cartridge here, cart.pce. And you can see here, we're just starting our emulator with the cartridge just here. Very straightforward, really. So that's how we can compile and run our program today. Pretty straightforward, really. So we've had a bit of a look at the PC Engine here. If you're interested in more PC Engine stuff, and I would suggest you possibly should be, but if you're not, fine. But quite why you're still watching the video, I don't know. But anyway, there's lots more videos on the PC Engine on my YouTube channel. Please have a look. There's a playlist related to PC Engine. There's content on the website. All the stuff you've seen today, totally available for download, so go to my website again. Anyway, I hope you found this interesting. If you've enjoyed this video, please like and subscribe because that's a big help to me. I really hope you've enjoyed it, and I hope you're going to enjoy programming the PC Engine. And if you're not interested in it, then please at least try playing some of the games because, as I say, they're far better than it got credit for in the West. Anyway, hope you've enjoyed this. Thanks for watching today, and goodbye.